All right, so we want to look at this example here dealing with this box as we talk about optimization. And again, what we're trying to do here is find a best solution for a scenario. Okay? Now, typically best is going to be either the highest possible or lowest possible. Okay? If we're talking about a business and we're looking at our costs, then the best solution is going to be the one that minimizes our costs. If we're looking at profit, on the other hand, then we want to maximize that. All right, so what we're really doing here is we're tying real-life situations back to what we were dealing with before when we were talking about absolute and relative max and min points. Okay? Absolute and relative max and min points, and depending on what we have, really what we're going to be doing is identifying an interval to use and then getting the absolute max or min within that interval. Okay? The challenge with these is kind of similar to the challenge that we had with our related rates, and that is really just figuring out what function we're dealing with in the first place. So let's check out this example here. A manufacturer wants to design an open box, so no lid, having a square base and a surface area of 108 square inches. What dimensions will produce a box with a maximum volume? Okay, so we kind of present the issue here. First of all, with the picture, notice if I have a square base, okay, we could call it x by x for our square base. And then we have the height as well. How tall are we going to make this box? And notice the top is open here. Okay, and that kind of a detail is very important to recognize because it said that we want the surface area to be exactly 108. Okay, if we had to count the top, then that's obviously going to impact things, right? Yes?
Doesn't taking the top off give it like a lot more surface area?
Yeah.
Well, you would not include the inside.
Okay.
The surface area we're talking about would be the outside surface area. So that's a good question, yeah. We would just be including the outside.
And you're going to include the little thing on top. Like,
And we're going to what? Oh, like the thickness?
Yeah.
No, that will, when you're talking about surface area, you're thinking about something in two dimensions. The thickness of this, you're talking about like how thick is this like panel or whatever.
Mm-hmm.
We would not include that because we're just not, you can either assume that it's not something that you would really put anything on, especially if this was like a cardboard box. That would be the edge that is like holes and stuff like that. Okay? So we would just look at the outer, all right, the outer part of this. Now, as you could see here, what we have is we have a surface area of x squared plus 4xh equals 108. Okay? Now, where did the x squared come from? That's the area of the bottom, okay? So this bottom part has an area of x squared, okay? So that's your x squared. Then we have the sides. Now, because this is a square base, all four sides are going to be exactly the same, all right? And each side is x by h. Okay, so this side is x times h. The side back here is x times h. The back side here is x times h. And the front side here is x times h. So there are four of them. That's why we have a 4x times h there. Okay? So that's the first thing. And what we were told is we want this to be exactly 108. Square units, okay? Square inches in this case. However, we can make this box in a lot of different ways. Okay? Here you'll notice they made the base 3 by 3, and that gave us 8 1/4 inches tall to make it. Okay? This box over here is 8 by 8, so that made it only 1 3/8 inches tall. And you can see here that the volumes are going to end up being different. Okay, depending on what dimensions we use for the box. Okay, someone pick another number. 6. Okay, all right, 6. So let's say that we made the bottom of this box 6 by 6. Okay, so this is 6 by 6. If x is 6, then we have 6 squared plus 4 times 6 times h equals 108. Subtract 36 and we get 72, 24, h, so h is 3. So it's 6 inches by 3 inches. Okay, 6 by 6 by 3. Now, how do we find the volume of this? It's volume of a box, right? How do we find volume of a box? Yeah, base times height times length, or however you, whatever words you want to use. It's the 3 dimensions multiplied together. Okay? So the volume here is 6 times 6, the area of the base, times the height. Alright, so 36 times 3 actually ends up being 108, but this is a volume, so that's cubic inches. Okay? So as you can see, there's a lot of different possibilities. Which one gives us the maximum? Out of all these, the one Paul just made here actually gives us the greatest so far. But this is what we need to do. We need to figure out if we're trying to maximize this volume, we need to figure out a function for the volume. Okay? So that's one of the things here that you have to get into your mind right away, is that when you are trying to maximize something, maximize volume, the function that you have needs to be V. Okay? Just like in our related rates, if you were trying to find the rate of change of the volume, you made your function equal the volume. Okay? So right now, though, we have the volume equals x times h. Okay? Or V equals x squared h. And if we're trying to find the max, we may think about taking the derivative at this point, right? So dv dt, or dv dx, sorry, would be, well, we're kind of stuck because we got 2 variables, right? Ah, okay. What'd you say, Sonny?
Use the G to solve the H.
Yes, okay.
S.
Yeah, we're going to use the surface area formula to write h in terms of x. Okay? Because here's the thing. I know you might be saying, well, wait, we could just do dv dt and do everything in terms of t. But we don't have any rates, and this box isn't, like, changing. Alright? We just want a maximum. So this isn't a rates problem. So we want to get everything in terms of the same variable. So what we'll do is we'll take this function right here, and we're going to solve it for h. So I have 108 minus the x squared equals the 4xh, and then I'm going to divide by the 4x. So that's going to make it, let's see, 108 divided by 4 is a 27 over x minus x over 4. I decided to do it in two different parts. All right, so that's my h. And now I can plug that in. Okay? X squared times 27 over x minus x over 4. And if I distribute that, that's actually really easy to take the derivative of. Okay? Notice here, before I just had a formula for v, now I actually have a function v of x. Okay? I have it in terms of one variable. Okay? Now, let's distribute here. 27 over x times x squared is just a 27x. And that's going to be minus x cubed over 4. And that's going to be my v in terms of x. So now, my dvdx, or v prime of x, is pretty easy. 27 minus 3/4 x squared. Okay? So now what? Now what? Set equal to 0. What are we trying to do? We're trying to find a max, right? Trying to find the max. So, set this equal to 0. I get x squared by itself, and I've got 27 times 4/3, so that ends up being 36. So x is plus or minus 6. So that's my solution, right? Yeah, we can't use -6. This is where our domain has to be considered. Okay? Theoretically, x could be infinitely big. We could make it a mile by a mile, and if this box was short enough, it would still have a surface area of 108. And, well, no, it wouldn't have a... We couldn't make it that big. Sorry, got carried away. But the volume, we could arrange this a lot of different ways. Let's think about the height has to be greater than 0 in order to have a box, right? So my height has to be greater than 0. So I could figure out what x would need to be. 27 over x would have to be greater than x over 4. Which means that, let's see, if I cross multiply here, I'd have an x squared has to be less than 108. Okay? So that gives me one boundary. X has to be less than whatever square root of 108 is, which would be 2 times 3, 6 root 3. Okay? But also x has to be greater than 0. Okay? So that's my domain. Not really for the function itself, but it's the domain for the situation. So oftentimes what I'll do is I'll call this the situational domain or logical domain. Based on the fact that this is real life, we have to work within the realm of reality. So this is what we've got. Okay? So that's why -6 is not a possibility. So the solution I want is x equals 6 inches. And actually, Paul gave us the best solution. Okay? So we just found our best solution. This is the kind of thing where you know, a company knows it costs a certain amount per square inch to produce the packaging, okay, for a certain a box or something. So they don't want the cost, they want the cost to be at whatever 108 square inches would be. But then we want it to hold as much as possible. Okay? So we could have made a box with these dimensions, but it'll only hold 74¼ cubic inches. But if we make the box with these dimensions, it'll hold a whole lot more. Okay? So, here are some basic guidelines as you're doing these optimization problems. Identify what you're given and what you're trying to find. Make a sketch when it's possible, okay? Listen, the sketch on a lot of these is really going to be important, especially if you don't remember your formulas from geometry, okay? You don't have to remember the formula for surface area of a box. You know, perimeter of the base times the height would be around the edges plus the area of the base. You don't have to remember that. If you see the picture, though, you know how to find areas of squares and rectangles, hopefully, and you can piece it together. Okay? Then, number 2, write the primary equation for the quantity that needs to be maximized. Okay? You've got geometry formulas. That's where we had the v equals x squared times h. Alright? Then you need to get that primary equation down to where it's in terms of only one variable. Okay? Theoretically, we could have made this v as a function of h, but that would have been annoying to work with. So try to do it the best you can with the simplest way possible. Okay? So there's where we solved for h using our other parameter, the surface area. Okay? Then make sure you pay attention to the domain. Here they call it the feasible domain, logical domain, realistic domain, okay? Situational domain, whatever it is, you got to consider what's possible. And then find the max or min value, okay, using your calculus. Okay? Does that make sense? All right. All right, so here's another one. It is an optimization problem. It says that we want the points on the graph of y equals 4 minus x squared that are closest to the point 0, 2. Okay? So here's where a sketch would be helpful. This is our parent quadratic function. It's been shifted up and reflected downward. Okay, so it's been shifted up 4 units and then it's reflected, so it's aiming down. So there's a sketch of that parabola, and we want the point 0, 2. So we've got to find the closest distance, okay, or the shortest distance. There's the optimization part, okay? Now, I want you guys to take a few minutes. I want you to work with the person closest to you, either behind or beside you, okay? And I want you guys to see what you can do with this for a few minutes before we look at any solution. All right, so let's take a look at, we actually have 2 different kinds of solutions, 2 different ways you could solve this. One takes a little bit more finesse, and you'd have to really kind of think about outside the box here. I'll show you that one second. The more straightforward method here is to think about what does it mean to be the closest. It means that our distance is the shortest. Okay? So if I want the distance between the point 0, 2 and some point on the graph, that's what I'm looking at there. Okay, I picked some random point on the graph where I have an x coordinate and then the y coordinate will be 4 minus x squared, because that's what the function is. And then remember, our distance formula is derived from the Pythagorean theorem. Okay? So this side here is x minus 0, and this side right here is the 4 minus x squared minus the 2. Okay, which is 2 minus x squared. Okay? That's where our distance formula came from. That's why we have this. Alright? So our distance now we could rewrite as d equals the square root of just an x squared plus 2 minus x squared squared. And now d is actually a function of x. I could even write it as d of x if I wanted. Okay? What I want here is a minimum value. Okay? I want the minimum. Now I know since this is a square root, the distance will never be 0. Alright? So I'm going to take the derivative, d of x, and that's going to be 1/2 times the x squared plus 2 minus x squared squared to the negative 1/2 power times the derivative of the inside. Okay? So the derivative of the inside is going to be the 2x plus 2 times 2 minus x squared to the first power times the derivative of the inside, which is a negative 2x. Okay? Now, some of you I saw had actually FOILed inside the 2 minus x squared squared and combined like terms. That may have actually ended up being easier. One thing to be careful with is that you'd have a positive x to the 4th. Minus 4x squared plus 1x squared would be a minus. You'd have x to the 4th minus 3x squared plus 4 would be if you FOILed that and combined the other x with it. That might make life a little easier, because then it would be what you would get inside here. You wouldn't have to do chain rule and stuff. It would just end up being a 4x cubed minus 6x, and that's it. Okay? Either way, you'll get to this. It's just a matter of how long it takes you. Okay? So I have that over the 2 from the half there, and also over this square root of x squared plus 2 minus x squared squared. Okay? That is my d prime of x. Does that make sense? Okay? So we found the distance formula. We took the derivative. And now we want to set this equal to 0. Okay? This is going to equal 0 when the numerator is 0. The denominator is never going to be undefined, because if I have something squared plus something squared, I'll always have a positive. So I don't need to worry about places where it's undefined. So I'm just looking at 4x cubed minus 6x equal to 0. So I take out a 2x, and I've got a 2x squared minus 3. So x is going to equal 0, or a plus or minus radical 3/2. Okay? So here comes our sign diagram. 0, negative radical 3/2, positive radical 3/2. I plug in different numbers into my derivative. the bottom will always be positive, so I don't even need to mess with that. I'm just looking at the numerator. And let's see, negative square root of 3 halves, that's square root of 6 over 2, which is going to be a little bit bigger than 1. Okay, or smaller than negative 1. So I can actually plug in 1 and negative 1 in those intervals. If I plug in a 1, I have 4 minus 6, which is negative. If I plug in a negative 1, I'm going to have a negative 4 plus 6, which is positive. If I were to plug in a negative 2, I'd have a negative 32 plus 12, which is negative. And if I plugged in a positive 2, I'd have 32 minus 12, which would be positive. So that's our first derivative, or I shouldn't use f, we're doing d, that's d prime. So that tells us that d is decreasing, then increasing, then decreasing, then increasing. Okay? So I have minimum values here and here. So where are we the closest?
Those 2 points.
Yeah.
It's actually going to be both. If you think about it logically, because of the symmetry here, both of them will actually be equal minimum points. Okay? So I've got the point negative root 3 over 2, and then 4 minus x squared is going to be 4 minus 3 halves. That's 2.5. And my other one is going to be a positive 3 halves.
I think your iPad just disconnected.
Yeah. There we go. So there we have it. The our 2 points where we are closest. Okay? Some of you use some good logic. Like, definitely, once we get to x equals 2 or negative 2, we can see that the distance is really getting much bigger. Okay? You know, if we were to go all the way to x equals 2, it's getting longer and longer the further we go. So we know it can't be too far away from 0. And hopefully you see the symmetry there too that tips you off to that. Okay? Now, let me give you the kind of thinking outside the box solution to this. All right? So there's another method that you can use here. But it takes making sure that you know how do you find the closest distance between a point and a curve. You draw the segment at what angle to the curve?
90 degrees.
90 degrees, okay? So in other words, if I were to take that same graph, let me sketch it again here. And here's my point 0, 2. And here's the point that I want, okay? The shortest distance will be when that segment there is at a 90-degree angle to the curve. In other words, it will be perpendicular to the tangent. Okay? So, when will that segment be perpendicular to the tangent? Well, I would need to have the slopes be opposite reciprocals. Good, okay? So here's my point x, 4 minus x squared. Here's the point 0, 2. Okay? The slope of that is going to be a 4 minus x squared minus 2 over x minus 0. That's the slope of the little distance segment that we've got. The slope of the tangent line is what? Slope of the tangent line is derivative, okay? So what's the derivative of 4 minus x squared? Negative 2x. So if I want to do perpendicular to that,
Must be 1/2. Maybe.
perpendicular, it would be 1/2 or 1 over 2x. Okay? Alright, perpendicular. Here's the slope perpendicular to the tangent, or we could say the normal. That's going to be 1 over a positive 2x. So guess what? If I set the slope of d equal to 1 over 2x, I should be able to solve for x, right? Let's try it. So I have a 2 minus x squared over x. There's my slope of d equals 1 over 2x. Okay, if I go ahead and cross multiply, I get x. Actually, let's not cross multiply. Let's just multiply by a 2x. So the x's cancel. Because I know x can't be 0. Alright. So that gives me 1 equals 4 minus 2x squared. X squared would equal 2, and x would be plus or minus root 2.
And we got that.
Hang on, did we get...
It's back to our favorite
equals
answer.
x. Right.
Did I mess something up there?
So we should be 2x squared equals 3. 2x squared equals, like,
Yeah.
Oh yeah, because we subtract, duh. Alright, 2x squared equals 3. We do the calculus, so we screw up the arithmetic. Okay? Alright, so 2x squared equals 3. So there's our plus or minus radical 3 halves. I was going to say, we should get the same answer. Alright, so there you have your plus or minus radical 3 halves. That one is a whole lot shorter, a whole lot less messy, but you had to really think outside the box in order to come up with it. Okay? So, but that's the cool thing about math. There's always, almost always, more than one way to solve it.